Hi again. We are doing section 7 point, not 7, 12.2. Sorry, I have no idea where that 7 came from. Section 12.2, which is an introduction to vectors. So like I said in the last section, you've probably seen everything we're going to talk about with vectors if you've taken physics or some other engineering course. But we're going to start with the basics. Not everybody has seen vectors, so if it is a review for you, just enjoy the ride for the next 2 or 3 sections. So a vector is just used to indicate. Oops, sorry, I'm drawing all over the screen. Used to indicate both a magnitude and a direction, and so you'll usually see this with a arrow on it. So like these couple arrows over here on the right hand side, these are vectors being graphed out. You notice there's an arrow on the end of pointing toward the B and toward the D. We usually denote a vector in print if it is bold, or we'll put an arrow over it. So you might see a vector with an arrow like this, or in a lot of the engineering courses or physics courses, they'll also use a hat. So you might see a hat. It kind of looks weird if you put it on a V, but if you have a vector I, might have a hat on it, or a J might have a hat on it. If you want to use the hat notation, that's perfectly okay. I usually use the arrow notation just because I come from the math world, not the engineering physics world, but that's just me. So for instance, suppose that a particle moves along a straight segment from point A to point B. The corresponding displacement vector, shown in this figure over here, has an initial point A, which is the tail, and a terminal point at B, which is the tip, and we would write vector V as the vector AB with a little arrow on top. And vector U would be CD, having the same length as vector V, even though it is a different position. So your magnitude and your direction would be your magnitude the same. Your direction, your position might be a little different. We say that U and V are equal or equivalent if they are the same direction and the same length. The zero vector has zero length with no specific direction, and is the only one that has no specific direction. And then down at the bottom, you'll notice this little blue box that says if you want to add 2 vectors together, if you take U and V are 2 vectors positioned so that the initial point and V is at the terminal point of U, you can add them together. That would be these 2 vectors over on the right hand side. And you'd end up with the sum of U plus V is the vector from the initial point of U to the terminal point of V. This also has a fancy name. It's also called the, if I can get the pen to write it, the resultant vector. So if you ever see, to find the resultant vector, that is the sum of the 2 vectors added together. We can do scalar multiplication. You can take 2 vectors, you can add them, you can subtract them, you could scalar multiply them pretty easily as well. So if a C value, a scalar, is a number, and the V is a vector, then you can multiply the vector by the number, and it just changes the length if it's the same sign, if it's a positive sign, and it will change the direction and the length if it is a negative sign. So your vector V, these 3 right here, are changing the length but not the direction. It's taking the V, the original V, and doubling it or halving it, but they're going the same direction. The last 2 are changing the direction, and on the very last one, the direction and the length. The difference between them is just adding the negative, which would be another addition. And so if we do this in 3 space, given the points x1, y1, z1, and x2, y2, z2, a vector A can be represented by just subtracting the x's, subtracting the y's, and subtracting the z's. And we use greater than and less than kind of notation on either side. It's not exactly the less than and greater than symbols. It just kind of looks like that. It's not parentheses. It's not brackets. It's kind of, looks like less than and greater than. So which one of these would be a vector and which one of these would be a scalar? So a scalar has to have just a value, but a vector has to have a value for the magnitude and also a direction that it might be going in. So for instance, the cost of a movie ticket, it doesn't have any direction associated with the cost of a movie ticket. This would just be a scalar. It's just a number. Whereas the river flowing, a current of a river, that could be represented by a vector. Because you would have the magnitude, the speed of the current flowing, and the direction that it's going. So you need a vector to show that. A flight from Houston to Atlanta could also be a vector. You need the direction going from Houston to Atlanta, and you might need the speed for the flight itself. Whereas the world population, that's just going to be a scalar. It's just a number, however how many people are in the world. So you do have to recognize the difference between what would be a scalar versus what would be a vector. Here, this parallelism says to name all the equal vectors in this picture. So equal vectors are the ones that have the same direction and the same magnitude, the same length. And so, for instance, the vector from A to B, connecting those two, that matches, you need a horizontal vector of that same length. That would be matching with D to C. Now, it does make a difference. We go from initial point to terminal point. So the vector AB and the vector BA are not going to be the same thing. So you do want to go from the starting point, the initial point, to the arrowhead of the ending point. So this vector here matches this vector here. Another one would be the other two sides. You have a vector going up and down on the left and a vector going up and down on the right. That would be vector dA. Oops, that's an A there. Would be equal to CB. We have two other sets. We have the one going along the diagonal. Oh, I probably should have picked a different color than the exact color that the parallelogram was. So you have this vector going from D to E and the vector from E to B. So D to E is the same as E to B. And then going the other direction, there's one going from C up to E, and also one that goes from E up to A. And so all of those are equal vectors with each other. So there's several of them that are equal. Okay, this says find a vector A with representation given by the directed line segment AB and draw those and starting at the origin. And so, for instance, this first one down here, point A is -2, 1, and point B is 1, 2. So if I want to come up with a vector A, oh, sorry, it says a little a up there. Vector A, and I'm going to use it with the little arrow on there. I subtract the x's minus the y's. So 1 minus -2, those are the x's, and I subtract the y's, 2 minus 1. That would be the vector 3, 1. That would look like this one. So the vector 3, 1, starting at the origin, is just a line segment going from this point at 0, 0 up to this point at 3, 1. So you can kind of see 3, 1 would be kind of like a point itself, and you're just connecting those 2 points. The arrowhead pointing towards the 3, 1 tells you the direction that it's going. Whereas the other vector, for part B, I would do 2 minus 0, 3 minus 3, and negative 1 minus 1. That would be the vector 2, 0, negative 2. So 2, 0, negative 2 would look like this. You're going over 2 on the x-axis, you're going down 2 on the z-axis, and it's actually in the plane. So you're not going left, you're not going up or down on the y-axis. So you're going over, this would be like 1, 2, and then you're going down 1, 2 on the z-axis. But you're pointing, this point right here would be the point 2, 0, 2, and that's the origin. Okay, like I said, you can add or subtract vectors. So if you take 2 vectors and add them, that's your resultant, and you just add each component. So whether you do it in 2 space, which is the top 2 ways, or 3 space, which is the bottom ones, you're just taking the first 2 components, adding them, the second 2 components, adding them, or the third 2 components and adding them, or subtracting them. The first one subtracted, the second one subtracted, the third one subtracted. Or you could do a constant multiple with a scalar, a c value, multiplying it on each one. Then we can figure out the magnitude or the length. The magnitude, represented a few different ways down here at the bottom, is the length of any of its representations and denoted by the symbol either an absolute value around a v or a double bar around the v. It's also called the norm of a vector. So if you ever see the norm of a vector, that would be the length or the magnitude. And all we have to do is use the distance formula that we looked at in a previous section to figure out the magnitude or the length. And so the distance formula would be with the second point being at 0, 0, 0. So this one says, find the sums of the given vectors and illustrate it geometrically. So we're going to add them together. So if I call this one vector A and this one vector B, and I wanted to add A and B, I would add the first terms and I would add the second terms. And so that would be 5 and 2. Now, if you do it geometrically, it would look kind of like this. The negative 1, 4, that would be this vector here. The B, the 6, negative 2, would be this vector down here. When you add them together, what you'd want to do is take one of the vectors and move it to connect them together. So I'm moving this A vector down here. Notice it's the same vector. I made it dotted just to show you that it's not technically sitting there. But if you were to move it, pick it up and move it down to there, then you would draw from the origin to the tip of that moved A to come up with your resultant. So this right here is your resultant vector, which should be the 5, 2. So if you go over 5 and up 2, that's your ending point right there. And so that would be your resultant. And I can do the same thing with B. If I call, let's do a different color. If I call this one A and this one B, then A plus B would be 3 plus 0, 0 plus 8, and 1 plus 0. Well, that's kind of nice, a bunch of zeros. So we get 3, 8, 1. And that would be my resultant. It would look like this. 3, 0, 1 would be this vector down here, the bottom one. This would be vector A. The one on the y-axis, the 0, 8, 0, this would be vector B. And it's kind of hard to notice, but vector A is actually directly above the x-axis. So this one's directly above. It would make a triangle there. And so this is actually kind of going up into the first quadrant. If you move this A around to here to connect the end point to the beginning point to the end point of vector B, this would point up to this point up here, which is the point 3, 8, 1. This diagonal one is your resultant. So hopefully the picture helps a little bit. If not, just add the numbers together. That's all you're really doing. And so that's what we'll do here. We're going to add them, the A plus the B, the 4A plus 2B, the absolute value of A, which is the magnitude, and then the magnitude of A minus B, and figure that out for the vectors -3, 4, and 9, -1. So if I add them, all I'll get is -3 plus 9 and 4 plus -1. And so that is 6, 3. Pretty easy, hopefully. 6, 3. 4 times A and 2 times B, that'll tell me I do 4 times A, which is the -3, 4, plus 2 times B, which is the 9, -1. So I would distribute the numbers across first, and so that would give me a -12 and 16, added to 18 and a -2. So if I add the first two together, -12 and 18, that would give me a 6. And 16 and the -2 would give me 14. And that would be my 4A plus 2B. The magnitude of A says I take the square root of each number squared. So I do -3 squared and 4 squared. So that's 9 plus 16, or 25. So the magnitude of that vector is 5. The magnitude of A minus B, you want to figure out what A minus B is, of course. And so A minus B would be -3 minus 9 and 4 minus -1. And so -3 minus 9 would be -12, and 4 and 1 would be 5. And so I want to find the magnitude of that vector. So I take -12 squared plus 5 squared, which is 144 plus 25. That'll give me 169, which is 13. So the magnitude of the two vectors subtracted comes out pretty nice as well. It comes out to a nice even 13. Now there's a lot of properties that go along with vectors, and you'll see this if you're in or already taken linear algebra. You do a lot of stuff with vectors in that class, and physics, and all sorts of classes have vectors in them. So if you have 2 or 3 vectors in this case, if A, B, and C are vectors in V sub n, V sub n would be called a vector space. You talk about that in linear algebra. And C and D are scalars, then if you add 2 vectors, it doesn't matter what order you do them in. If you add 0 to the vector, it doesn't matter. It doesn't change it. If you group them together, it doesn't matter if you do B plus C first and then add A, or if you do A plus B first and then add C. If you add the negative of the same vector, you'll get the 0 vector. If you do a scalar, it doesn't matter if you put the scalar on each one first or add them first. And all of these properties are things that you've heard about with just numbers anyway. Commutative property, distributive property, associative property. just like 3 plus 2 and 2 plus 3 both give you 5, that sort of thing. So all the properties that you kind of know from numbers work in a vector space as well. And then you have your Ijk vectors. These are very popular in your physics engineering type classes. The vector I is the vector 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. And so we could write every vector in what we call Ijk notation. A unit vector is a vector whose length is 1, just like the unit circle is called the unit circle because the length, the radius of the circle is 1. So same idea. So for instance, Ijk are all unit vectors because each one of them has a length of 1. You either go 1 in the direction of the x-axis, the y-axis, or the z-axis. So in general, if you have a vector that's non-zero, then the unit vector that has the same direction as the original vector A would be to multiply that A by 1 over the magnitude. Or you could just do the vector divided by the magnitude. That would be the same thing. That's called a unit vector. And we'll do a lot with unit vectors. So this one says, find the unit vector that has the same direction as the given vector. So you have the vector 6, negative 2. So my unit vector, so if say this is vector A, my unit vector is A divided by the magnitude of A. So that's 6, negative 2 divided by the square root of 6 squared plus negative 2 squared. And so that's 36 plus 4. That plus sign looks a lot like a T, so I'm going to try that again. But the 2 squared is 4. So I get the square root of 40. Or, that does simplify to be 2 root 10. And if you want, you could actually simplify this a bit more by dividing the 2 that's in front of the root 10 into the 6 and the 2, just as a scalar multiple. And you could make this say 3, 1 divided by the root 10. Or you could go even further. You could write it as 3 divided by root 10 and 1 divided by root 10. It just depends on how far you want to go. Any of these on the bottom would be acceptable answers for the unit vector. I'll do the same thing with vector, with part B down here. I'll call that vector B. Notice this one's an Ijk notation, which is okay. That would be the same thing as the vector 8, negative 1, 4 if you wrote it in the other notation. But my unit vector, in this case, would be that vector 8i minus j plus 4k divided by the square root of 8 squared plus negative 1 squared plus 4 squared. So I have the 8i minus j plus 4k divided by 8 squared is 64 plus 1 plus 16. Ooh, this will come out kind of nice. This is 8i minus j plus 4k. 64 and 16 is 80 plus 1 makes 81. And I can do the square root of 81. That's just 9. And so I could say this is 8i minus j plus 4k divided by 9. Or you could divide the 9 into each one. If it's in Ijk notation, I do tend to divide the number on the bottom into each one, just because I think it looks better to say 8 divided by 9i minus 1 divided by 9j plus 4 divided by 9k. I think that looks better than leaving the whole thing over 9, but it doesn't really matter. So hopefully that's not too bad. This says find the vector that has the same direction as 6, 2, negative 3, but the length is 4. Since you don't know what the length is, anyway, the easiest thing to do is to take that vector, turn it into a unit vector that you know has a length of 1, and then just multiply that vector by 4 to have a length of 4. So that's what I'm going to do. I'm going to find a unit vector for 6, 2, negative 3 by taking that vector and dividing it by its magnitude, where I take each one of those numbers, add them together after I square them. So I'll have 6, 2, negative 3. On the bottom, I'll have 36 plus 4 plus 9. I don't know if this one's going to come out quite as nice as the last one did, but 36 and 4 is 40 plus 9 is 49. Hey, it does come out as good as the last one. That's kind of nice. So this is 6, 2, negative 3 divided by 7. Or you could say your unit vector is 6 divided by 7, 2 divided by 7, negative 3 divided by 7. It is kind of nice to notice that if it comes out to a nice number like 7, that means that the original vector had a length of 7, right? And so you could have multiplied the original vector by 4/7, and you could have come up with the vector that way. But anyway, find the unit vector. That's what we have here. And then I want a length of 4, so I want to do 4 times the unit vector. And so 6 times 4 is 24. 2 times 4 is 8. And 4 times negative 3 is negative 12. Oops, sorry. It is not a parenthesis. It is supposed to be a thing like that. And so this would be a vector in the same direction that has a length of 4. Okay, this says what is the angle between the given vector and the positive x-axis? And so, in case you don't remember, this would be a trig kind of idea. So you'll have to use, just like what we did back in trig, tangent theta equaled y over x. We talked about that a little bit in chapter 10 as well. So when you divide y over x, you've got a angle. Well, the b and the a are going to be treated just about like your y's and x's would be. So if I have a vector I plus root 3j, or if you'd rather write it, this is 1 and square root of 3 for the vector, whichever one you want to do, then I could do that tangent theta is the second number divided by the first number, or just root 3. So this says, where does tangent equal root 3 off of the positive x-axis? Well, off the positive x-axis, that's going to give you either quadrant 1 or quadrant 4. This would give you a quadrant 1 angle since it's a positive root 3, and tangent is root 3 at pi over 3. And so that's what they're looking for, what your rotation would be. Or 60 degrees if you'd rather do 60 degrees. A lot of the times your vectors and things will do it in degrees instead of radians. So one of those two answers. Or the 8 and the 6, that one won't come out quite as nice. This is the same thing as vector 8, 6. So when you do your tangent theta, you would do 6 over 8. Well, it does simplify. It's, oops, sorry, not a 2. It's a 3. 2 goes into each one. 3 over 4. That is not a number off the unit circle. And so in that case, you pretty much just have to type it in the calculator. And so you would type it in as tangent inverse of 3 over 4. And I'm just going to tell you the angle in degrees. You can change it to radians if you want to, but it comes out to 36.9 degrees. Like I said, most of the time degrees are actually more useful in vectors than radians are. Okay, if vector v lies in the first quadrant and makes an angle of pi over 3 with the positive x-axis, and you know the magnitude of that vector is 4, what is the actual vector itself? What is vector v? What are the components? And so you'll need a couple of formulas for that. And we have a couple of formulas. The first component is given by the magnitude times cosine of the angle. The second component is given by the magnitude times sine of the angle. And so our vector v will have the first component, the a, would be the magnitude, which is 4, times cosine of the angle, which is pi over 3. And my second component of my vector is my 4, my magnitude, times sine of the angle, which is pi over 3. And so vector v, cosine pi over 3 is a half, and sine pi over 3 is root 3 over 2. And so my vector v turns out to be 2 and 2 root 3. So if you know the magnitude and you know the angle that it makes, you can find out what the actual vector was. Or you could go the other way around. You can find if you have the vector, you can figure out the angle and the magnitude. Okay, how about this one? If a child pulls a sled through the snow on a level path with a force of 50 newtons exerted at an angle of 38 degrees above the horizontal, what are the horizontal and vertical components? Well, that's what we literally just did. Our vector would be the two components. I know that I have a force of 50 newtons. That's going to be my magnitude. And then I have an angle of 38 degrees. So I would do 50 times cosine 38. And you would definitely have to do this in the calculator. You're not going to get a 38 degrees off of a unit circle or something. And then I would do the magnitude times the sine of the angle, just like we did on the previous problem. And so typing those two things in the calculator, 50 times cosine 38 is 39.4. And 50 times sine 38 is 30.8. So your first component is the horizontal component. The second component is your vertical. So our horizontal component is 39.4 newtons. And our vertical component is 30.8 newtons. And that would be the force acting on that sled. And I'll show you a couple more kind of like that. A quarterback throws a football at an angle of elevation 40 degrees and a speed of 60 feet per second. What is the horizontal and vertical components of the velocity vector? I do the exact same thing. The first one is my magnitude, and here my magnitude would be my speed, 60 feet per second, times cosine of my angle, 40 degrees. And then the other component would be based with sine, 60 sine 40 degrees. And again, you just have to put these in the calculator and see what they come out to be. 60 times cosine 40 is 45.96. 45.96. And 60 times sine 40 is 38.57. 38.57. So the horizontal would be the first one. We have 45.96 feet per second in velocity horizontally. And our vertical component is 38.57 feet per second in the in the vertical direction. And that would be your components for your velocity vector. Okay, how about one last problem? A woman walks due west on the deck of a ship at 3 miles per hour. The ship is moving north at 22 miles an hour. Find the speed and the direction of the woman relative to the surface water. Okay? So we need to come up with basically a vector to work with here. The woman is moving west, and the ship is moving north. So pretend like if we had it on an XY plane, I might say north would be straight up, west would be going this way, east would be going that way, and south would be going that way. But pretend like this is a XY plane. Well, she's walking west at 3 miles an hour, so that would be the negative x direction. And then the ship is moving north. That would be the positive y direction. So I'm going to let my vector be the vector of the ship, which is the 0, 22, going due north. And the woman walking west would give me negative 3, 0. So I have negative 3 and 22 for my vector v that I want to work with. I need to know the magnitude of that vector. So the magnitude would tell me the speed. And so if I do the magnitude, I would have negative 3 squared plus 22 squared. Now, negative 3 squared is 9. That one probably everybody knows. 22 squared is a little harder for most people, but it's 484, if I remember my 10th grade math correctly. And so I add those together to get 493, which that's not going to be a perfect square. So we're going to approximate that. It's about 22.2 miles per hour. That's the speed the woman's walking relative to the surface of the water. And then we need the direction. The direction, I just need to find the angle for that vector. So I'm going to do tangent theta is the y over the x, or the b over the a. So I'll get that theta is tangent inverse of negative 22 thirds. If I do negative 22 thirds, I'll get an angle of about 82 degrees, or actually negative 82 degrees. This is about negative 82 degrees. Now the problem with that negative 82 degrees is negative 82, if your east is at 0 degrees, so negative 82 is going down this direction, rotating clockwise. I need to be, because she went west and north, I need to be in quadrant 2, not in quadrant 4. And so I need to rotate this angle back around the other direction. I need this angle to go this way. So I got to rotate this angle back around by 180 degrees. So I need to add 180 to that to get it back in the right spot. And so 180 and the negative 82 gives me 98 degrees. So 98 degrees would be the direction she's walking in. But 98 degrees is not usually how they would say it. And so what they would say is, in bearing is done a little bit differently than your angles from trig. If you're doing bearing, your north is up here at 0. And you would go north and then east or west, one way or the other. Our angle is here. So we're actually 90 degrees would be straight up and down usually. We're going to 98. So this little angle right here is 8 degrees. So her bearing is north and then 8 degrees west. So you could write it that way in bearing, or you could just say it's 98 degrees. Kind of depends on what the homework would, or the quiz or whatever would ask, whether it's in bearing or if it's just the angle itself. The angle itself is 98 degrees. She is going at the angle of 98 degrees, but that is north and then 8 degrees west. So hopefully that makes sort of sense. That's 12.2. We're going to go into 12.3 and 12.4. If you've seen it in vectors already, you've probably definitely done the dot product and the cross product. That's the next two sections that we'll be working with.